Okay, guys, welcome to Physics 203, Class 29. And we're going to continue with our study of special relativity with looking into dynamics, which involves momentum and energy. And this is going to be a quite interesting extension of our phenomena that we've seen so far in terms of length contraction and time dilation, addition of velocities, and so forth. Because we'll find that our classical expressions for momentum and energy have to be modified in light of um, Einstein's postulates and the postulate of special relativity. So first, let's look at what the one of the problems is. Um, we know that in classical physics, one of our favorite tools is F equals ma, force equals mass times acceleration. That was Newton's second law and the heart of his system of motion. But and here's Newton here. Newton's second law works well at low speeds that we're used to, but since Newton's law says that a is, which is the derivative of the velocity, dv dt, is equal to F over m, that's just a rearrangement of F equals ma, a constant force, F, will keep increasing the velocity, and there's nothing in principle to stop that from happening, so it eventually could increase it above the speed of light if enough time elapses. Okay, so if we just put a force on something and continue that force for enough time, we can wind up with a velocity above the speed of light. And that's something Einstein said couldn't happen. So just for a definite example, if we have an electron, okay, here's an electron between capacitor plates, starting from rest, and let's say the electric field is 1,000 newtons per coulomb, which is easily achievable between capacitor plates, we would have dV is equal to F over m dt. That's solving for dV here, F over m dt. But for a particle, a charged particle, F is QE. So we'd have QE over m dt. And we're interested in when since the particle starts from rest, the change in velocity would be equal to the speed of light. When would we reach the speed of light? So we can solve for that amount of time, dt, as just m multiplying through by m and dividing by QE, mc over QE, plugging in m for an electron, c, the charge on the electron in coulombs, and our electric field, we find a time of only 1.7 times 10 to the minus 6 seconds, or 1.7 microseconds, to first reach and then afterwards exceed the speed of light. So with electrons, since they're so light and very quickly, we could, if classical physics is correct, violate Einstein's postulates that nothing can travel faster than the speed of light. So what can we do about this? Well, to fix this, we can view Newton's second law, first of all, in the form that he actually wrote it, which is F is equal to dp dt, where p is the momentum, m times v. And if we plug in m times v here, we get, and m is constant, we can pull out an m and we just get m dv dt, or ma. But to fix this problem, we have to modify the classical expression for the momentum, p is equal to m. Now here I'm going to use the book, and I am going to use u for the velocity of the particle to distinguish it from v, which we've been using as the relative velocity between reference frames. So when you see u, just think the velocity of the particle. U is the velocity of the particle. So several arguments outlined in the text, which I won't get into, but which you can certainly look at, indicate that the following form for the momentum p will rectify this problem of things going faster than the speed of light. And the form is this. P, the momentum, is equal to gamma, our gamma factor, times mu. So it's just our classical momentum mu times the gamma factor. And the gamma factor, remember, is 1 over the square root of 1 minus the velocity squared over c squared. So this would be mu over 1 minus u squared over c squared. So why does this work? Well, as the velocity u approaches to c, u over c will get closer and closer to 1, as will u squared over c squared. So this denominator will get closer and closer to 0. And so the denominator approaches 0. The momentum then, as u approaches c, can keep increasing as force is applied without u ever increasing past the speed of light. Okay. So as u approaches c from below, this denominator will approach to 0, and the momentum can get larger and larger and larger, and so the force can keep increasing the momentum, F equals dp dt, without the velocity u exceeding the speed of light. Okay, and this is just a picture to illustrate this. We can see that as u as a function, as u as a fraction of c increases, classically, the linear momentum, as the moment to achieve a high momentum, we have to reach velocities above c. But relativistically, we can get the momentum as high as we want with velocities v over c less than 1, that is, velocities less than c. So this is our new and improved expression for the momentum, the relativistic momentum. It's gamma, just the gamma factor times the classical momentum. Okay, so we have momentum. What about kinetic energy? Well, the work energy theorem from classical physics, from physics 201 in our case, tells us that the change in kinetic energy of a particle is given by the work. So the work in going from position 1 to 2 is the integral from 1 to 2 of f, well, normally it would be f dx, but here we're allowing f to be vectors, so it'd be f dotted with ds. So this is what we call a line integral. But nevertheless, it's basically the product of the force times the distance would be equal to the difference in the kinetic energies. That's the work energy theorem. So we can try applying that here with our relativistic force, which is dp dt, where p is our new momentum, gamma times our classical momentum, acting on a particle from rest. And if we do that, we find, writing the position, change in position as the velocity times the time interval, the work would be equal to just k, since we start at 0. So the work is just equal to the final kinetic energy here, since we start with k1 equal to 0, would be the integral of the force, which is the derivative of the momentum, our new momentum, gamma m mu, dotted with our displacement, ds, which is our velocity times time. Okay, so this would be our expression here. And integrating this expression is a bit technical, and it's done in the textbook, or it involves an integration by parts. I won't go through the details of that here, but if we integrate it, we get a relativistic expression for the kinetic energy, which is given by mc squared times gamma minus 1. Okay, so mc squared times gamma minus 1. One thing to notice about this is that if U is equal to 0, so if we go back for a second, if U is equal to 0, the gamma factor is just 1, okay, because gamma is the square root of 1 minus U squared over C squared. So when U is equal to 0, it would be 1 over the square root of 1 minus 0, or 1, okay? So when the particle's not moving, gamma is equal to 1, and we just get the kinetic energy equals mc squared times 1 minus 1, or 0. So it matches up when the particle's not moving. The other interesting thing about this sort of funny looking expression is it doesn't look as much like the classical expression as the momentum did. For the momentum, it was just the gamma factor times the classical momentum. But here, this doesn't look a whole lot like our classical expression, 1/2 times mu squared, 1/2 mu squared. Remember, u is the velocity. But if u is much less than the speed of light, we can actually show that the classical expression, 1/2 mu squared, approximates our new relativistic expression for the kinetic energy very closely. So how does that work? Well, here's the expression for the kinetic energy written out, where gamma is written as 1 over the square root of 1 minus u squared over c squared, minus, so multiplied out, mc squared times minus 1 would be minus mc squared. And then we do something to this funny expression here called a binomial expansion. And it's basically derived from a Taylor series. We take this expression and write it as an approximation in powers of a small quantity. And the small quantity here is u squared over c squared. Since we're talking about low speeds, the speed u squared over c squared would be very small. And so the Taylor series for this expression, 1 minus u squared over c squared to the minus 1/2, turns out to be 1 plus 1/2 u squared over c squared plus terms of higher order, u to the 4th over c to the 4th, and etc. But those will be very small because u squared over c squared is small itself. Okay, so that's a Taylor series to make this expression more manageable. Okay, so then let's multiply this out. We get mc squared plus 1/2, and the c squareds cancel here, 1/2 mu squared minus mc squared. So we have mc squared plus 1/2 mu squared minus mc squared, and we just get 1/2 mu squared, which is the classical result. So as long as u is much, much less than the speed of light, this new expression for the kinetic energy will match up with our classical expression for the kinetic energy. And again, here's a graph showing for u over c, in order to achieve kinetic energies above a certain level, we have to go to velocities greater than c, which is not physical. So if we keep pouring energy into a particle, eventually our velocity will exceed c. But relativistically, if we graph this expression versus u over c, we find that we can get any kinetic energy we want, as high as we want, and the velocity is, u is limited at the speed of light. Okay, so that's kinetic energy. Now we can look at total energy and conservation of mass energy. We can rearrange our definition of kinetic energy to solve for mc squared times gamma, and that's going to just be equal to k plus, we multiply here, we have minus mc squared, and bring that over to the left side. We get mc squared gamma is equal to k plus mc squared. And we interpret this This is the kinetic energy, of course, that's what we defined it as. Um, we interpret this as the total energy, mc squared times gamma, is equal to k plus some type of energy which is still present when there's no kinetic energy. And so we interpret, as I said, the symbol E equals mc squared gamma as the total relativistic energy, which is the sum of the kinetic energy and mc squared. But what is this mc squared? Well, if the kinetic energy is zero, the object's not moving, it must be an energy that's just associated with the mass. So even when an object is at rest with u equals 0 and gamma equal 1, we have E equals mc squared. That's the famous formula that Einstein came up with. Here we call it E naught to indicate the velocity is 0, and that's called the rest energy. And m is called the rest mass. Okay, so through this reasoning, that E is equal to, or that a particle has energy even when it's not moving, Einstein showed that mass is a form of energy and vice versa. And so, for example, a proton is made up of quarks. Okay, quarks are little particles that are inside the proton. There's two up quarks and a down quark, and some interactions between them. And so the energy, the proton has an energy which would be made up of its three quarks energy plus their mutual potential energy. Okay, plus the interactions. All of these would contribute to the overall energy and therefore the overall mass of the proton. So the proton is part the energy of its individual quarks and part the energy of their interactions. All right, because of this, instead of conservation of mass and energy separately, because mass and energy are related so closely, we think of conservation of mass energy as one quantity. So as an example, when uranium decays into several byproducts and gives off energy as it does in a nuclear power plant, because it's giving off energy, the products must have slightly less mass than the original uranium, so that mass energy is conserved. Another example, interesting example, is if we have two masses m. So these two objects are moving at each other with speed v, one to the left and one to the right, or sorry, one to the right and one to the left. Let's get that straight. And they stick together with a compressed spring clamped between them. Okay, so let's analyze this in terms of what we know about the total relativistic energy and the conservation of mass energy. The mass energy before would be each of them, since they have mass m, has rest energy mc squared, and they would each have the same relativistic kinetic energy, which would be mc squared times gamma minus 1. So the mass energy before would be 2mc squared plus 2k. Okay. The mass energy after would just be E, since these particles are moving in opposite directions, their momentums will cancel and they will just join together, and therefore they will be at rest afterwards. Okay, since their momentums cancel, they're just going to lock together and their final momentum will be 0. So there's no kinetic energy afterwards, so their mass energy after will just be equal to their mass m, whatever it is, times c squared. But the mass energy E is conserved, right? That's what we've said. The mass energy is the new conserved quantity. So we have the mass energy afterwards, the total relativistic energy afterwards, mc squared, equal to 2mc squared plus 2k, okay? But that means that big M must be greater than 2m, because k is greater than 0. So this side is greater than 2mc squared. So that means that mc squared is greater than 2mc squared, 2 little mc squared. So m is greater than 2m. So that means that we've gained some mass here. And where is that mass coming? Well, there must be some energy in that new system, and it's the potential energy of the spring. The spring has been compressed, it has potential energy, and that would contribute to the final mass, big M, okay? So our total mass here would be the rest masses of each of these together plus 2k, because the 2k gets converted into potential energy in this spring here. Okay, all right, so we wind up. So we've seen E equals mc squared, and that seems to be the big idea. But I'd like to argue that there's a relationship which is more useful and general than E equals mc squared. Okay, imagine that. So since both are conserved, our total relativistic energy and our relativistic momentum are very important quantities. Is there any way to relate them? Okay, it'd be great if they were related to each other, since they're both conserved in any interaction, and that would be very useful in analyzing what happens to particles in collisions and so forth. It is possible to relate them, and a derivation in our textbook, it's on page 66 if you'd like to look at it, shows that we can relate these two. And we get the expression E squared is equal to P squared C squared plus M squared C to the fourth. Okay? So let's look at this for a second. This applies to any situation, but there are two special cases here which are very interesting. The first is when P is equal to 0, when the momentum is equal to 0. Okay? In that case, the object is at rest since its linear momentum is 0, and P is equal to 0, so we have E squared is equal to M squared C to the fourth, or taking the square root, E is equal to MC squared. Okay? So we just get the connection between the rest mass and the rest energy, okay, when P is equal to 0. So this equation up here, the E squared equal P squared C squared plus M squared C to the fourth, contains E equals MC squared in it. But it also contains another interesting expression. If M is equal to 0, in this case, this term, the second term, drops out, and we get E squared equal P squared C squared, or E is equal to the absolute value of P times C. That is, E is equal to plus or minus P times C. And the only massless particle we know of is the photon, the particle of light. So this would be the relationship between the energy, the relativistic energy and momentum for a massless photon. So this equation contains that as well. So I would argue that maybe instead of E equals MC squared, we should put on our t-shirts this E squared equal P squared C squared plus M squared C to the fourth. So what do you guys think? It doesn't roll off the tongue quite as easily as E equals MC squared, so I doubt it's going to sell many shirts, but it's something to think about. Okay, so what have we learned this class? We've learned that we have to generalize our definition of momentum relativistically to include the gamma factor. We've learned our relativistic kinetic energy can be found from the relativistic momentum, and that it agrees with the classical kinetic energy at low speeds. we have defined the total relativistic energy as the kinetic energy plus the rest energy, which is E equals mc squared. And we've seen that the rest energy contains both uh, smaller masses and the potential energy of interactions between them. And we've seen that we can relate the total relativistic energy and the momentum. So I hope you found this first introduction to relativistic dynamics interesting, and I will see you all in class.